The oxidation state is a charge on the atom in the molecule. And then what is formal charge? If the oxidation state is a charge on the atom, then formal charge is what?
The charge of the whole thing as a whole?
The whole charge of the net charge?
The net charge.
And so the formal charge would just be plus 1 for this. Is that correct?
No, that's true. No, because oxygen has 2 double bonds. So
Well, this is showing formal charge of oxygen. The formal charge on oxygen is 0. Well, what is formal charge? If the oxidation state is the charge, then formal charge can't be the charge, can it? Yeah, Manny, you know?
Isn't the oxidation state the average apparent charge and the formal charge is the actual charge of the individual atom?
Could be. That could be. What do you think of that? The oxidation state is the average charge on the atom? The average of what? So if I'm looking at the oxygen, you tell me the oxidation state on this oxygen.
It's 6 minus.
This structure is totally wrong.
Yeah, that's what I was saying. Like,
Yeah.
it's more than 8.
Yeah, this structure is ridiculous. Unfortunately, sorry. This is from Petrucci.
That was the truth.
I didn't even notice it. Really. Yeah, this structure is ridiculous. Why is this structure ridiculous?
Because
2, 4, 6, 8, 10.
there's an extra.
Oxygen can't have 10.
You could, can you force
We
it?
need to remove 2 of these lone pairs.
I think they forgot to remove it.
Yeah, you see, what they did was they took a lone pair from the terminal atom and dropped it into the bond here, and they forgot to erase it. And so the actual structure is this. The actual structure is going to have 2 lone pairs now, a double bond. Oops, this is oxygen.
Yeah.
And then the nitrogen, and then the double bond here. Now this would be right. But you guys remember how to calculate oxidation states, right? What are the oxidation states that we have here?
Okay.
What's the oxidation state of this oxygen?
Oh, -2.
-2.
And nitrogen is +4. And oxygen is again -2.
Okay, that oxidation state is the average of what, though? If you're saying it's the average charge, what did we average to get -2? Did we average a -1 and a -3? A -1 and a -3 will give us a -2. But, so it's an average of what?
Well, of its typical charge.
Of its typical charge? Typical charge is -2, so the average of that would be -2. Would be the typical charge.
And then it holds on to the electrons from nitrogen. Yeah, in order for that to work, it has to be +4. Because it's basically holding on to the electrons because it's more electronegative.
Is it an average based on percent abundance?
No, that would be the mass.
That'd be nice.
Yeah. The atomic mass of oxygen would be the average based on its abundance. This is hard to come up with. Does somebody else have a definition for our oxidation state?
Wasn't it the assumption that it's 100% ionic bond interaction?
Yeah, exactly.
What was that again?
The assumption that it's 100% ionic bond interaction.
It's assuming that the bonding's 100% ionic, so really the structure should look like this. When we do oxidation states, this is the structure we're going to generate. Nitrogen is not +4, sorry, is it?
5.
Yeah, it's +5. The sum of the oxidation states is equal to the net charge. plus. So nitrogen's plus 5, and then if we assume that this were ionic, this is what it would look like, right? And this would be the charge on each atom if this were ionic. Correct? There's a formula for oxidation states that looks very much like this. There's a formula in chapter 3. The oxidation state is equal to number of valence electrons. Remember that? But that's the formula for formal charge. So what's the difference between formal charge and oxidation state? When you look at the formula, you know, some people, I ask them, what is formal charge? They just write that equation. Does the equation tell me anything, really? It tells me how to calculate it, but does it tell me anything beyond that?
But it doesn't know.
Because if you look at that equation, do you need to know any chemistry, really, or much chemistry to do a calculation like this? No. But just because you can do this calculation, you know, doesn't mean you know anything. In fact, just because you can calculate an oxidation state doesn't mean you know anything. You could know nothing about it and still do it. Right? And so what you do, what you want to do is you want to know something about it, because that would be much more valuable, you know, as far as knowledge goes, and as far as skills go. And so looking at this equation, is that a good definition for formal charge? No. This is not a good, this is just an easy way to calculate it. This is an easy way to calculate and still not know anything. And so can you look at the equation and tell me what that equation is telling you in words? What that means? I can calculate the formal charges. We can calculate the formal with the correct structure. That's the incorrect structure. The formal charges we circle. So the formal charge is going to be 0, plus, and 0. Those are the formal charges. So we have two competing charges here. And so what does the formal charge tell me? Yeah, exactly. Formal charge is calculating the charges assuming 100% covalent bonding. So if we assume what does 100% covalent bonding mean? It doesn't mean winner take all. Winner takes all in ionic bonding. In covalent bonding, what we're going to do is we're going to split the electrons evenly down the middle. And so this oxygen ends up with 2, 4, 6. This nitrogen ends up with 2, 4. If nitrogen ends up with 4, it's 1 short of its valence. This oxygen ends up with 6. Well, oxygen is okay with 6 because it normally has 6 valence electrons. And so we don't normally show the 0. Both of these are 0. We just show the positive. And so what we're seeing is two extremes. The two extremes are this. We can assume the bonding is 100% ionic, we generate these charges here. We assume that the bonding is 100% covalent, we generate these charges. Well, which is correct? Is it 100% ionic, or is it 100% covalent? Which one is correct? It turns out that neither is correct, right? Neither is correct because it's not 100% ionic, nor is it 100% covalent. I mean, you can see it here. NO and nitrogen is a 3.5. Oh no, oxygen. Let's see, what is it? Fluorine's 4. Oxygen's 3.5. Nitrogen is 3.0 actually. And so the delta En is 0.5. Delta N is 0.5. It's kind of down here. It's almost non-polar. Right? Actually, it's closer. It's much closer to this. Because oxygen and nitrogen are close versus this. So it's much closer to this, but even then, there is some ionic character to this. And so the utility of this is the picture isn't this, nor is it this. It's somewhere in between. So what we want to do is we want to look at the two extremes, and these are the two extremes. So the charge on oxygen is going to vary from 0 to -2. It's going to be somewhere in there. And so what we call that is, since we don't have a number, we just call it delta minus. You know, the charge on oxygen is somewhere between 0 and -2, and I don't have that number, so I'll call it delta minus. The same thing over here, delta minus. And then usually we have a delta plus for the nitrogen. But in this case, the nitrogen, the minimum charge on nitrogen is not a partial charge. The minimum charge is a full positive. And the maximum charge is +5. So the charge is going to be somewhere in between these two. Does it make sense? And so we do this. We do formal charge and oxidation state to get an idea of the two extremes and the charges they generate on the atoms. And so we want to do formal charge. Well, we did oxidation states. Oxidation states are very handy for talking about redox chemistry. But formal charge is very useful when talking about Lewis structures and acid-base behavior. And so let's take a look at formal charge applied here. We can see here, the positive formal charge circled here, these are 0 and 0. This is the correct structure, actually. They got the lone pairs right there. This thing has a net charge, so when it has a net charge, and there are two ways of calculating the net charge. The two ways are this. The net charge, which is +1 here. Net charge equals 1, the sum of the oxidation states. So if I look at the oxidation states, -2, -4, +5 is +1. Sum of the oxidation states. Or we can calculate it using 2. It's the sum of the formal charges. If we sum up the formal charges, it's 0 + 1 + 0 is +1. And so the net charge is either the sum of the oxidation states or the sum of the formal charges. They both should give us the same number. Let's look at this. This would be called an alternate structure. Rather than making two double bonds, what we could do is we could make a triple bond and a single bond. If we make a triple bond and a single bond, look at what happens with the formal charges. The formal charges go from 0 to +1, so we lose a lone pair here in the bond, and over here we create another lone pair here, so we get a negative. Now when I look at this formal charge distribution, it's unstable. The reason it's unstable is, look, I have this oxygen here, this oxygen here. One oxygen takes an electron from the other oxygen. Does that sound right? If there's a tug of war between two oxygens, it should be a tie, close to a tie. But in this case, this would be an unstable formal charge distribution. It's unstable because of the separation of charge here. And so this structure isn't good. What's better is having the two double bonds. And so we want to minimize the formal charge here. So again, the sum of the formal charges is the overall charge. The formal charges should be as small as possible. Negative formal charges, usually on the most electronegative elements, formal charges of the same size on adjacent atoms is unlikely. Okay, not only that, this looks weird. You know, one oxygen wins over the other oxygen in a tug of war for an extra electron. But this is also weird. Two atoms with the same charge. If we have two atoms with the same charge, they're going to not attract each other, they're going to repel each other. And so this is going to be unstable as well, having adjacent positive charges, as well as adjacent negative charges. So we don't see this. This would be unstable. Sometimes what we'll see, I'm going to stop pretty soon. Sometimes what we'll see is that we have choices here that are equivalent in energy. So I could have made the double bond on the left here. Everything has an octet. But I can't get rid of the formal charge. I mean, if I try to get rid of the formal charge, it seems like it'd be easy. I can get rid of the formal charge here. Like, for example, here, I have one oxygen a loser, one oxygen a winner, but these two oxygens are different. Do you know the difference? This oxygen is what we call a bridging or central oxygen. This oxygen we call a terminal oxygen. And so, you know, they aren't exactly the same. If they were exactly the same, it would make no sense. Like, for example, in O2. If I had O2, then I wouldn't have one oxygen positive and the other oxygen negative. There are only two oxygens here. And this wouldn't happen. But something like this might happen because, you know, even though you think oxygen, what's electronegativity of oxygen? If we go back to the table, electronegativity is 3.5. But do you think both of these are 3.5? No, both of these aren't 3.5. And so this is why Noe's question about the table comes about. Because if I looked in the more advanced table of electronegativities, I'd see a bridging oxygen has a different electronegativity than a terminal oxygen. And so otherwise we treat these the same and it'd be a tie, and how could this happen? You know? But you know, it doesn't have to happen because I got an easy fix for that. If I just make two double bonds, then I don't have to worry about it. All right, if I have two double bonds like that, then there's no formal charge. Okay? And so if I do two double bonds like this, there's no formal charge and everything looks good. 2, 3, 4, 5, 6, yeah. But does this structure look good to you?
No, the central atom oxygen has an extra pair of electrons.
Yeah, well, you know, counting up the electrons, I have 18 electrons here. You know, 3 times 6, 18 electrons. And so I have to have that extra pair of electrons there. And so it's not that it has an extra pair of electrons. Oftentimes it will have an extra pair of electrons. The problem is what?
It's not stable.
This is not going to happen because it has more than an octet. This central oxygen has more than an octet. 2, 4, 6, 8, 10. 10 electrons. We can't have it on an octet. So there's no choice. We have to have a formal charge here. And in ozone, we have it. But when we look at this here, we could either have the double bond on the left or the double bond on the right. Actually, both structures are fine, and both are going to have the same energy. But in reality, when we measure this, we see that both bonds are equivalent. And there isn't a polarization in the electron cloud. Like, for example, if the double bond's on the left, then we expect more electron density over there, less over here. Not only that, we have a negative charge and a positive charge. A negative charge should show up as red, a positive charge should show up as blue. Do we see that here? Well, a little bit of blue here, but maybe a little bit of red there. But when we look at it, we should have red here on this one, and then it should flip. And so there should be red here. And so does the red flip back and forth? That is that. No, it doesn't. The negative charge does not flip back and forth. It does not resonate. Instead, what we have is this. Do you recognize this? What's this thing called? This thing is called a resonance hybrid. And so the actual structure isn't one of these. These are resonance forms. The actual structure is a resonance hybrid. And the way to understand this resonance hybrid is like this. It's like water in a tub. If we have water, let's say like this, let's look at this first structure on the left. We have twice as much electron density. The electron density we'll call the water. And so let's say we have 2 feet of water over here. And then over on the right side, we have 1 foot of water. We can sustain this. We could have 2 feet of water here and 1 foot of water here as long as there's a barrier that prevents the electrons from moving. But it turns out, do you see these arrows here? These arrows show what's called a mechanism. And the mechanism can show how the electron density can move around. And that is here. If I take this lone pair and take these and drop it into the bond, well, I get more than an octet. But if I kick these out, I get back to an octet. And so these electrons come in, these electrons come out. And then when that happens, we switch to this structure. That is, we'll move the double bond here. But with the double bond over here, what I can do is I can just reverse this, bring this pair down back into the bond and kick these out here. And so there's a mechanism for electron density to move within the molecule. If there's a mechanism, what that means is that there's no barrier here. And that is, we cannot sustain 2 feet of water here and 1 foot of water there if the electrons can move. That is, if the water can move. If the water can move, then what we're going to end up with is not 2 feet and 1 feet. We're going to have 1.5 feet of water here and 1.5 feet of water here. And so this is what we call the resonance hybrid. And so what happens is the electron cloud spreads out like water. And so rather than being a double or a single, turns out to be a 1.5 bond, or a bond order of 1.5. This is a 1.5 bond. And then when I look at the negative charge is distributed over 2 atoms. So each atom is going to have a negative 1/2 charge here. And so you can just see the slight red, and it's very symmetric here, and then the slight blue here. And so that's the hybrid structure. So we'll go on to this. These are we can't have more than an octet. For example, on oxygen, carbon, or nitrogen, but we can have less than an octet. And there are different bonding configurations that we can have. So this has less than an octet on carbon. Carbon has 2, 4, 6, 7, so it's 1 electron short. We call this a free radical. In fact, all these are free radicals. And when we have a single electron like that, we call it a dangling bond. It wants to bond to something else, like another hydrogen here, or hydrogen here. And so this would be called the methyl radical. This is the hydroxyl radical. This would be the nitrosyl radical. So sometimes those form, but those aren't stable. Sometimes we have less than an octet, even though it looks like we can complete the octet. So for example here, boron has less than an octet, but if we make a double bond, so we take this lone pair, bring it into the bond here, then we can get an octet. So the problem with this is the formal charge. The formal charges here were all 0. Now we're going to have a positive formal charge on fluorine, and boron's going to have a negative formal charge. It should be circled. Formal charges are generally circled. And so here, but there's a problem with this. If there's a tug of war between fluorine, which is a 4O, and boron, which is a 2O, who's going to win? Fluorine or boron? Fluorine. Fluorine should win. Who won in this structure? Boron won. So it doesn't make sense. And so this structure does not exist. Even though we could get the octet, we're going to keep it at less than an octet, because fluorine isn't going to want to give up an electron to boron. Ignore that structure for right now, but that makes BF3 quite reactive. And so BF3 is shy of an octet, and so it can participate in Lewis acid-base reactions. Lewis bases are electron pair donors, like fluoride. BF3 is electron pair acceptor. So it turns out that BF3 is a powerful Lewis acid, and it can take another fluoride here and then generate this structure, BF4 minus. Now, the fluorines are going to have 0 formal charge. Boron's going to have a negative formal charge here, which is not shown. And so this is okay. This is okay here. Now, what's going on here? Do you see what they're doing here? They're making one of the bonds ionic. So what is it? Is the bonding ionic in BF3, or is it covalent? Well, this is non-metal and non-metal, so we tend to think of it as being covalent. And then delta En. But delta En, what is delta En here? Boron's 2, fluorine's 4, delta En is 2, which means
It's like right at
it's right at the border. And so, well, we aren't going to talk about this until later. And so we'll skip it for now. Why are they showing only one of the bonds as ionic? Shouldn't all 3 bonds be ionic? If all 3 bonds were ionic, then this would be fluoride, 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 and boron would be what charge? Plus 3. All right. Well, I said that nitrogen, oxygen, carbon, those can't have more than an octet. But once we go to the third period and lower, like phosphorus, sulfur, and lower, so under nitrogen and phosphorus, we can have an expanded octet. So here we have 2, 4, 6, 8, 12. This is PCl5. PCl5 exists. You can buy the stuff. It's fairly stable. But this is going to have an expanded octet. Sulfur, this is SF6. SF6 is stable as well. In fact, the sulfur-fluorine bond is very strong, so this is fairly inert. And this is an expanded octet. So we can have more for third period and beyond. But for second period, it just doesn't do this. We aren't going to have an expanded octet. Sometimes we expand the octet to maximize bonding, like SF6 and PCl5. Sometimes we expand the octet to lower the formal charge. So if you look at the formal charges here, they're -1 on all the oxygens, +2 on the sulfur. But if we create 2 double bonds, we can drop the formal charges to just -1 on these 2 terminal oxygens here. And so we could leave it as an octet with formal charge, or we can expand the octet to minimize the formal charge. In general, if we can expand the octet to minimize formal charge, we do it unless it's like one of the earlier examples here. Unless it's like NO2, or ozone. Ozone, we can't expand the octet to minimize formal charge. O3, we saw earlier. And so what I want you to do for start is to draw all the resonance structures for this and the resonance hybrid. And so how many resonance structures can we draw for this? Well, the resonance structures are just going to be variations of where we place the multiple bonds. And so in that structure, we have the double bond top and bottom. We could also have the double bond top and left. If we have the double bond top and left, we're going to end up with a structure that looks like this. We sum up the formal charges, we get the net charge. The net charge is 2 minus. And so how many of these can we draw? Now, that's 1, this is 2. We show these with a double-headed arrow, that they're resonance forms. So 1, 2, then how many more? And so why don't you draw out all the resonance forms for this and then the resonance hybrid, and then we'll start again after that.